So the goal of this study that I'll talk about today was to look at, try to understand better the seasonal cycle of sea surface temperature in the northeastern tropical Atlantic. Rick Lumpkin and Claudia Schmidt are my co-authors on this, and we recently wrote it up, and it's in press now and in Journal of Climate, in case you want more details. So it's a really unique part of the world ocean, I think, the northeastern tropical Atlantic. And one of the main reasons is that there's a constant stream of aerosols, mainly dust from Africa and smoke from the Sahel region. And you can see in this picture is taken during the last T&E cruise. It's between about 15 north and 25, somewhere between 15 and 20 north, a few hundred kilometers off the coast of Africa. You can see the haze during the day, so it's kind of a gloomy place sometimes with the haze from all the aerosols. It's also a pretty poorly understood part of the ocean, and one main reason is that until recently there haven't been a lot of direct observations in this region. So kind of part of the motivating factor for the study. But, okay. So brief outline. I'll give some motivation for wanting to understand the seasonal cycle in the northeastern tropical Atlantic, and some background on previous studies that have looked into the seasonal cycle in this area. And the data, which is mainly observational, satellite, and in-situ data that I use. Seasonal cycle, briefly, just the kind of large-scale seasonal cycle in the tropical Atlantic to get started. And then the main focus is on quantifying heat budgets to determine the processes driving SST on the seasonal timescales. And the most interesting thing to me is the residual, the heat budget, and trying to interpret it in terms of physical processes, namely vertical mixing and entrainment, and then summary at the end. Okay, so part of the motivation is that we have two main modes of variability in the tropical Atlantic, and they're modulated seasonally pretty strongly. The first one is the Atlantic Nino mode, and it peaks in June, July, pretty strong peak. Warm SSTs in the east and enhanced rainfall, the shading. The meridional mode, so this is similar to El Nino in the Equatorial Pacific. The meridional mode is more north-south, warming in the north relative to the south. Doesn't have a really strong analog in the Pacific, and the winds are directed toward the anomalously warm hemisphere. So it tends to peak in the boreal spring for SST, which is the light colored bars, and wind peaks a little bit earlier in the winter, the dark colored bars. So both of these modes have important implications for climate on the surrounding continents, and especially the meridional mode and the SST in the tropical North Atlantic. So this shows a positive meridional mode composite, the coloring of SST anomalies, so warming in the North Atlantic, and opposite for negative AOML phase. The contours are vertical wind shear, so reduction in wind shear when the SST is warm and an increase in wind shear when it's cold, and this creates a lot more cyclones. The circles and the other symbols here, the circles, colored circles, the filled circles are the major hurricanes, so a lot more activities are in positive phases of the meridional mode. And it also affects rainfall. When you have warming in the tropical North Atlantic, it tends to draw the IPCZ anomalies to the north, and it can create strong drought in northeast Brazil. A recent study shows that if there's anomalous warming in the tropical North Atlantic during boreal spring, this tends to create, or it tends to favor the development of La Nina type conditions in the Equatorial Pacific during the summer and fall. So there are lots of reasons to understand the tropical Atlantic sea surface temperature and climate variability. And zooming in, especially in the tropical North Atlantic and the Northeastern Atlantic, this shows the mean SST on the top, strong meridional gradient of SST cooling to the north, and then the middle shows the standard deviation of the seasonal cycle of SST. There's strong variability, seasonal variability in the northeastern tropical Atlantic, and the interannual variability, shown on the bottom, mimics very closely the spatial pattern of the variability of the seasonal cycle. Again, suggesting that we really need to understand the seasonal cycle if we want to understand the interannual longer timescale variability of climate in the tropical Atlantic. So the region that we focused on is in the Fox area. That's what we focused on for satellite, Argo, large-scale analysis, and then the moorings. There are PIRATA moorings at each of the 4 triangles in that region that we also use. Okay, so more motivations that coupled models really don't do a very good job in the tropical Atlantic for the most part. There are large biases. It shows SST bias from CCSM4 relative to observations, well-known warm bias in the Eastern Equatorial Atlantic, and cold bias to the north. This is the latest version 4 of CCSM. It's somewhat improved over CCSM3, but still large biases. And it's actually worse if you look, there's a warm bias now developing on the southern part of this box in the northeastern tropical Atlantic, up to about a degree too warm and then too cold to the north. So the idea is if we can have some in situ observations and some analyses of the heat budget, hopefully we can start to improve these coupled models and make them more useful for understanding climate and for climate prediction in the tropical Atlantic. Okay, so that was motivation for understanding the seasonal cycle. There have been some studies that have looked at the seasonal cycle in the tropical Atlantic in terms of what affects the sea surface temperature. One of the most recent ones was et al. In 2006. They used mostly a statistical analysis looking at correlations between the rate of change of SST and the surface heat flux based on satellite and reanalysis data, and they showed that based on these correlations that the heat flux tends to drive SST to the north and to the south, and then ocean dynamics play a more important role where you see the shading. And this is just based on correlation, sort of a seasonal cycle. And there's one problem I have with this is that there aren't many degrees of freedom, so it's hard to use correlations to say anything concretely about what's driving SST. And then it's also unclear what ocean dynamics are involved. And I mean, ocean dynamics could be important off the equator, especially if they vary either in phase or directly out of phase with the rate of change of SST, because this is just a correlation analysis. So we want to try to get a more quantitative analysis of what's driving the SST. So there have been some studies recently focused along the Equatorial Atlantic. Luano et al. Looked at an ocean model and showed that the rate of change of SST, the cooling during boreal summer, was caused mainly by turbulent mixing at the base of the mix layer, this cooling here, and then to a lesser extent in November, December, a secondary peak in the mixing. And the heat flux is tending to oppose this cooling from mixing. It was always positive. Hummels et al., recent paper that came out, they did somewhat different analysis, looking only at observations of microstructure along the equator in the Atlantic at 10 degrees west, and they showed that there's a strong seasonal cycle to the mixing, shown as the red line here, with cooling of about 100 watts per square meter during the summer. And you really need this cooling to balance the heat budget. So the gray shading, the gray line is the rate of change of heat storage, and the black line is the sum of the forcing without mixing, and then when you add in the mixing, you get a really good agreement with the rate of change of heat storage, suggesting that this mixing is really important. And so there's some consistency here between the observations and the model, which is good to see. Okay, another issue, people haven't really looked at the possible role of vertical processes like mixing and entrainment off the equator, mainly because large-scale analyses show that the heat flux is well correlated with the rate of change of SST. But this shows the barrier layer thickness, the gray shading. So the barrier layer is when you have a fresh layer near the surface, a shallow fresh layer embedded in a deeper isothermal layer, and this tends to reduce the rate of turbulent cooling because the temperature that you're entraining into the mixed layer is about the same temperature as the mixed layer. So when you have a thick barrier layer, it tends to reduce the cooling to a solid line. Every time the barrier layer gets thick, it reduces the cooling. And so this could play an important role in the seasonal cycle of SST in the tropical North Atlantic. This is in the central tropical North Atlantic. Another study shows that the barrier layer can get pretty thick in the northeastern tropical Atlantic. This is about 15 to 30 degrees west based on direct observations from the cruises in Argo, showing a thick barrier layer up to 40 meters between the equator and 10 north during the fall, and it's a little bit farther north, around 20 north in the spring. So this could potentially be an important mechanism in the northeastern tropical Atlantic. Any questions? Okay, so you got a free preview of the rest of the talk. All right, so that's the motivation and some background to the data that we actually used in this study of the profiles of temperature and salinity and pressure from Argo. Individual profiles. We calculate mixed layer depth, barrier layer thickness, and depth of the 20-degree isotherm from the individual profiles, and then map it to 1-degree grid and monthly resolution for 2001 to 2012. There's a number of other data sets, mainly satellite data. The shock flux surface heat flux. This is monthly data based on satellite and reanalysis, a combination, 1-degree grid, PMI SST, and precipitation. So the bold here are the data that we use directly in the heat budget calculation. The PMI SST, Oscar near surface currents, and chlorophyll concentration, monthly climatology. This is just to get the penetrative component of the shortwave radiation. Reanalysis, the MERA reanalysis, this gives us decomposition of the shortwave solar radiation into the total, the clear sky, which is due to everything except clouds. Clouds are removed from the clear sky. The clean sky has aerosols removed, and the clean clear sky has aerosols and clouds removed. So we can look at the different components of the shortwave flux. Notice aerosol optical thickness and the quickscat surface winds. And we use the 2001 through 2010 period, since this is when all the data sets are available. So this is kind of a large-scale analysis based on Argo and satellite data. And of course, we know that there can be biases and problems with satellite and reanalysis data sets. So we really want trying to get some ground truth for the heat budget from direct measurements from moorings before PIRATA moorings. So each one, the data availability from each one is shown on the right, going from 20.5 north down to the equator. It's mainly for the P&E moorings, the 3 northernmost moorings. It's mainly data through 2006 or 2007 going up until the present. And on the equator, we have a much longer time series going back to about the year 2000. Subsurface temperature, black, salinity, red, horizontal velocity 10 meters from the current meter, and atmospheric shortwave, long wave air temperature, relative humidity, wind speed, and rainfall, which we don't use in this study. And then on the equator, we also have an ADCP that gives us current up to about the 30-meter depth for several years on the equator. Okay, so that's the data, and so we've covered the first two, and now I'll look really briefly at the seasonal cycle, and then get into the quantitative heat budget and look at the causes of the residual next. All right, so heat budget, and I've shown shown a lot of information here, so I will just pick out the most important features. So shown April and September. April is kind of the southernmost extreme of the IPCZ, which is why I picked that, and September is kind of the northernmost extent of the IPCZ. So there's a real big contrast between these months. In April, warmest SST is near the equator, rainfall, the white contours, high rainfall, and this all shifts to the north during the summer and fall, up to around 5 to 10 north. Solar radiation is the colors here, and as you might expect, it's the lowest values under the IPCZ, where there's a lot of cloudiness, and higher values to the north. And it shifts, everything shifts to the north of the IPCZ in the fall. So that's the atmosphere. The ocean thermocline depth is the color shading here, and it's shallow throughout the year in the eastern basin, and there's a strong seasonality about between the equator and 5 north due to the northward movement and the southward movement of the IPCZ. So the Guinea Dome, the shallow thermocline here, occurs on the IPCZ as farthest to the north, and there's excellent pumping driving up the thermoclines, and then it shifts more to the south, putting the strong seasonal cycle. The currents are mainly westward and pretty weak within this northeastern region, except strong eastward flow from the NECC in the fall. The barrier layer thickness has a strong seasonal cycle. You can see the large values, the colors here, up to 40 meters or so during the spring to the north, and then much weaker in the fall. And in the 0 to 5 north band, there's a strong barrier layer thickness in the fall and weaker in the spring. Contours are mixed layer depth, which is pretty uniform to the south, and a stronger seasonal cycle up to the north. So there's clearly a strong meridional dependence of most of the terms in the tropical Atlantic, which justifies taking the zonal average across this region, and we'll look at the meridional dependence with time for the seasonal cycle. And first, we need to know what we're calculating in the heat budget. So the main terms are the mixed layer heat storage rate, the surface heat flux, latent absorbed shortwave, long wave, and sensible heat fluxes, horizontal advection in the mixed layer, and the residual terms. This has vertical mixing and errors from the other terms. So this is just the storage rate minus these two terms. The mixed layer depth uses a 0.1 criterion in the shallowest measurement, which is about 5 meters for Argo and 1 meter for the PIRATA moorings. The currents are from Oscar, geostrophic, Ekman, and shear dynamics. And temperature is from TMI SST to get the gradient for the advection. And the residual then is an estimate of the mixing in the heat budget. So this is for the Argo and satellite analysis, and then the PIRATA analysis, we do the same thing, except we use direct measurements from the moorings for most of the terms. The only thing we use was the same for both analyses is the gradient, horizontal gradient of SST used to calculate advection. Everything else is independent. So there are really two independent analyses with the satellite-based analysis and the PIRATA mooring-based analysis. All right, so the heat budget based on this equation that I just described. This shows average, again, in the 18 to 28 degree west region off the coast of Africa in that box. And it's a latitude on the y-axis going from 5 south to 25 north, and the seasonal cycle calendar month on the x-axis starting in January. So the heat storage rate is showing strong warming, and the annual mean is removed from these to make it easier to compare them. So there's strong warming in the summer, cooling in the winter, north of about 10 north. Farther toward the equator, it gets a little more complicated with a semi-annual cycle due to the IPCZ movement, the dots here are its location. And solar radiation agrees pretty well with the heat storage rate in at least to the north of about 10 north. The contours here are the absorbed short waves. So it's very similar. The mixed layer depth is not having a big influence on the amount of short waves that's absorbed. The latent heat flux is somewhat weaker in terms of the seasonal cycle, but it's similar seasonality north of about 10 north, with a reduction in latent cooling during the summer and an increase in the winter due to wind speed changes. Weaker winds in the summer as the ICCZ is to the north, and cooling in the winter. So if we combine the heat flux terms, this is what's shown here, and then the bottom panel show each of the terms on the right-hand side here, the heat flux, horizontal advection, and the residual. And it looks like, if you just did a correlation, it looks like the surface heat flux agrees almost perfectly with the heat storage rate, suggesting that it's driving most of the SST variability at most latitudes. But there's a pretty big difference in the amplitude of these two, and this shows up in the residual. So there's pretty strong cooling during the summer and fall, and then warming, or relative warming, relative to the annual mean during the winter. So for the rest of the talk, we'll just focus on briefly looking at the major terms in the heat budget, which appear to be the solar radiation and the residual, and to a lesser extent the latent heat flux. So we'll look at the solar and the residual, starting first with the solar, and then the main focus will be on understanding this residual, whether there's actually physical processes that can describe the residual. Watts per square meter, so it's about going from negative 100 to 75 here for the colors, and this is just the annual mean removed. So it's, really strong seasonal cycle to the north.
When you say annual mean removed, that's annual mean as a function of latitude?
Right, yeah, so at each grid point, we remove the annual mean, and then just average across 18 to 28 west as a function of latitude. Okay, so surface solar radiation has a really strong annual cycle, especially in the north, and this decomposes it into mainly the zenith angle, plus really small water vapor and trace gas contributions, cloud cover, and aerosols. So in the north, it's mainly the zenith angle. The sun goes to the north during the summer, and then south of the equator in the winter, driving the strong annual cycle. Cloud cover is more important near the ICCZ, especially just to the north of the ICCZ. And aerosols really don't play a big role, at least for the seasonal cycle, compared to the movement of the sun and the clouds near the ICCZ. All right, so the rest of the talk will be focused on the residual, trying to understand it. And the first guess might be that it's modulated by changes in the vertical temperature gradient associated with the barrier layer, which has been shown to have a strong seasonal cycle in this area. So the right here again shows the residual latitude versus time for calendar month on the x-axis. The strong cooling in the summer here and less cooling in the winter, and a more semi-annual weaker cycle to the south. The barrier layer agrees pretty well with the residual, especially in the north. So there's a thinner barrier layer here, which would be conducive to stronger turbulent cooling, allowing more colder water up into the mixed layer, and the thicker barrier layer would also tend to produce weaker turbulent cooling during the winter. And it looks like it kind of works to the south with the thinner barrier layer, stronger cooling, and weaker cooling, thicker barrier layer. So this is kind of the first guess of what might be driving the residual. And we focused on these two regions, the trade wind region to the north and the ICCZ core region to the south, where the ICCZ is located, to try to better understand the residual in these areas. All right, so this is area average values in this trade wind region here, the bold box, and also from the mooring at 20.5 north, 23 west, which is the line here. The main point is that these agree pretty well. The area average based on the Argo and satellite data, and the mooring data from the single point at 20 north, 23 west. Strong annual cycle of solar radiation and latent heat flux. And there's a residual, the dotted line, the cooling peaks in the summer and fall, and also some indication of peaking in the summer and fall for the mooring analysis. There's a lot more noise for the mooring analysis because it's a point location and we have less data available. The time series is shorter, but generally there's good agreement here. So we can conclude tentatively that maybe the residual here is due to physical processes and not just errors in other terms of the heat balance. And if we do the same for the IPCC core region, the southern box here, and here we have a mooring, a P&E mooring at 4 north, and again, they agree reasonably well, considering we're doing an area average and then just a point location from the mooring. Semi-annual cycle of shortwave, balanced by latent during the late summer, this piece here. And the residual, again, the strongest cooling tends to occur in the spring. And again, in the mooring analysis, seems to be occurring mostly in the spring. And again, a lot more noise in the mooring analysis because of the point location, but generally they agree pretty well. So again, we have hopes that maybe we can interpret the residual as physical, in terms of physical processes and vertical mixing maybe in this region. Okay, so we need to, but to help with interpretation, it'd be good to have some kind of a physical reasoning, physical model to explain why we have more mixing during some seasons than during other seasons. So we look at the diagnostic model Miller and Krauss, and it's pretty involved. So I tried to simplify it by putting in pretty colors. So the blue is the blue is wind. This is friction velocity Q. This is an empirical constant. Then the rest, the red is surface buoyancy flux. So that's P0. Mixed layer depth is H, and another constant here in N. The penetrative solar component. This is proportional to the surface solar radiation. Gamma to -1. Inverse of gamma is the penetration depth of solar radiation. And then it's all scaled by buoyancy jump at the base of the mixed layer, and the current shear at the base of the mixed layer, where this is another empirically determined constant. So physically, if you increase the wind speed, you increase the entrainment velocity or the mixing. If you increase the negative buoyancy flux, for example, you cool the surface, you tend to increase the mixing. If you concentrate the solar radiation closer to the surface, then you will increase the mixing. And this is because the mixing occurs at the base of the mixed layer, and if you heat at depth in the mixed layer more, you stabilize it and tend to reduce the mixing. So if you concentrate near the surface, you tend to get more mixing at the base of the mixed layer. The buoyancy flux, if you increase the buoyancy difference, buoyancy jump, if you increase that, of course, you're going to decrease the mixing. And if you increase the shear, you will increase the mixing at the base of the mixed layer. So it all kind of makes sense. But we're not going to use that complicated equation. We're just going to simplify it drastically and test whether the mixing is proportional to just the wind. So just take this wind and then assume delta B is constant over the seasonal cycle, and the current shear is constant over the seasonal cycle, and that gives you friction velocity cubed over the mixed layer depth. We can take that, multiply it by temperature gradient at the base of the mixed layer, or temperature jump, reflecting the cool water being pushed into the mixed layer, and we get the total turbulent heat flux at the base of the mixed layer. And delta T is very difficult to determine exactly, so we'll just use qualitatively say it's related to the barrier layer thickness. If the barrier layer is thicker, you reduce the upward flow of mixing of cold water, and thermofine depth, if it's shallower, you tend to cool more into the mixed layer. So how does this all work out? It's very simplified. So the top shows the residual which I've shown before, area averaged in the trade wind region and the ICCZ core region. A strong annual cycle with largest cooling during the late summer and fall, and a much weaker seasonal cycle of the residual in the ICCZ core region. The middle shows the terms that we expect to control delta T. The barrier layer, the black, and the thermocline dust. They agree reasonably well. The barrier layer, at least, the thickest here when you have the weakest cooling associated with the residual. Doesn't work out quite so well in the like November, December, but generally it's in phase. Thermocline dust, not really in phase as well. So the bottom shows then the other part of the turbulent cooling term, the wind mixing, and I've taken a negative sign so that negative values mean stronger mixing, which would tend to cool, so it would be in phase with the residual. Strongest mixing during the early summer, and this generally agrees with the phase of the residual. So if you combine, the wind mixing and the barrier layer looks like this is possibly explaining the seasonal cycle of the residual. Stronger mixing in a barrier layer, and you get more cooling. In the ICCZ core region, it appears to be mainly changes in delta T. The barrier layer is thinner. The thermocline dust is shallower in the spring, causing more cooling, and then less cooling during the rest of the year when they're both thicker. And wind mixing is pretty constant throughout the year. So the main conclusion here, it looks like it's mainly delta T, barrier layer, and thermocline dust controlling the residual possibly in the ICCZ core, and wind mixing modified by the barrier layer thickness in the trade wind region, based on the simplified analysis. Yeah.
Trade wind region, is that a north of YTC?
Is it what? North?
Where is it located?
Yeah. So it's, yeah, 15 to 25 north.
What's the time of the wind data?
The wind data?
Yeah, time of
It's daily. The satellite, let me think what we use for wind. Yeah, quick scout. So it's daily averaged. Yeah, so we're not resolving the diurnal cycle, but otherwise everything should be resolved. Along the equator, so that was kind of to the north, 15 to 25 north, and then in the ICCZ region. Along the equator, we expect the dynamics to be a lot different because we have the strong south equatorial current, westward flow, and the strong eastward flow of the equatorial undercurrent, and there's known to be shear, which induces mixing and causes cooling possibly along the equator. So we wanted to look at this separately. And so this is kind of a large scale, what's going on, which I already showed. There's cooling in the summer along the equator, and strong annual cycle solar radiation, less so for latent. And the residual has kind of a weaker seasonal cycle with cooling during the second half of the year. This shows the mooring, the 023 west mooring from PIRATA. The data from that mooring and the heat budget agrees pretty well with this larger scale analysis. Solar radiation is highest in the second half of the year. Weak latent heat flux variability, some cooling from advection, which you also see there during the middle of the year, and a large residual. So this is without the annual mean removed here. And you can really see the large annual mean residual up to about 100 watts per square meter during most of the year. Looking at more detail at the residual, the black line is the red line is the residual, and the black line is the current shear at the base of the mixed layer, averaged in the mixed layer minus 20 meters below the mixed layer. And they tend to agree pretty well. There's really large error bars on the residual, but there's some agreement that it tends to be strongest residual, strongest current shear. This is the negative of the current shear, sorry. So negative residual, more cooling, stronger current shear. in the summer and again in November. The thermocline depth doesn't appear to be playing a role at all in this, and it's mainly the wind forcing. So in the spring and summer, the westward winds accelerate. You get stronger cooling from mixing due to the wind. And again, in November, we have a secondary acceleration of the wind driving the second peak of mixing in November.
But you said it's a shear.
Right. Yeah, this is shear. The black line here is the current shear at the base of the mix layer, and this is just friction velocity cubed divided by.
Oh,
so this is yeah, right. So it looks like the winds are driving the currents, which are producing the shear, and the wind may also be causing some local turbulent mixing in the mix layer. So these three, the current shear, residual, and local wind mixing all seem to agree pretty well.
Those are from the Equatorial ACT record?
Yes.
Climatology of the shear.
Yes. So we have about 3 or 4 years total, I think, of ADCP data, which is why, I mean, there's large error bars, but I don't know how, I mean.
They only get really for about 30 years from the surface, usually the upwards of
There's a current meter, yeah. There's a current meter which we use to help get the surface.
I guess it's not just the local wind that is important for generating shear, it's the wind all of the greater in Atlantic. So if I have the pressure gradient, and then
Yeah.
we just have the current and the current.
Yeah. Yeah. Yeah, that's true. I agree. This is very simplified. I mean, we need more modeling analysis to verify it. But it looks like, based on this, it looks like a large. I mean, I don't want to read too much into it because of the error bars, but I mean, if you believe this at all, a large part of it's the local wind forcing, causing, accelerating the surface currents, increasing the shear, and causing local mixing. That's the interpretation based on this. Okay, so there have been recent previous studies, which I've already shown. Actually, I've showed these earlier, but just to compare, Hummels et al., which use microstructure measurements, also showed stronger mixing, stronger cooling from mixing in the summer, the red curve. And Giuliano et al., using an ocean model, showed stronger mixing in the summer and a weaker secondary peak in November, December. So this is at 10 west. So the lines here, this is 10 west corresponding to Hummels et al., and 23 west corresponding to our study in the PIRATA mooring. So, I mean, there's some agreement. We also show stronger cooling from mixing associated with the residual during the early summer, and a weaker peak in November. And we agree with Giuliano et al. They also argue that it's mainly the wind forcing the circulation, which increases the shear, and the local wind mixing that drives the turbulent cooling. So we tend to agree with this analysis, and also with the microstructure agrees pretty well. The only difference is the microstructure doesn't really show the secondary peak that the model shows at the later part of the year. But of course, microstructure measurements they're tough to get, and they aren't not really well resolved in some areas, so that might be possibly why we have the difference. But it's good to see at least some general agreement between the different observations and the model. All right, so one more thing that we can do to try to validate that the residual is actually due to physical processes. We can estimate the mixing coefficient, which is this deep budget residual in our case, divided by the temperature gradient at the base of the mix layer. We assume it's a temperature at the base of the mix layer minus 10 meters below the mix layer for PDZ. And what we get is a lot of variability in the mixing coefficient, but a mean of about 2.2 in the trade wind region, 15 to 25 north. The ICCZ core, similar variability, and a weaker mean in the mixing coefficient, And this range generally agrees with what we found in the Indian Ocean ICCZ, which is encouraging. On the equator, the KV is, again, lots of variability and a mean of 3.7. And this generally agrees with what was found in the Equatorial Pacific Ocean for the seasonal range. And if you look at the annual means, just compare them, the trade wind region, kind of in between the ICCZ, which is very small mixing coefficient, and on the equator, a large mixing coefficient. So it all kinds of fits together. You'd expect the weakest mixing under the ICCZ, stronger under the trade winds, and strongest on the equator where you have the strong current shear. Summarizing, so we looked at the heat budget to start, and the heat budget showed a strong annual cycle in this trade wind region to the north. So this is here depicted. This is with the annual mean removed. So you get warming relative to the annual mean from the shortwave and latent during the May through August. And this is, I've chosen these periods. This kind of leads up to the northernmost position of the ICCZ, and this leads up to the southernmost position of the ICCZ. So there's warming as the sun is the farthest north, and it's counteracted by more cooling from turbulent mixing. On the equator, there are strong trade winds. This causes stronger currents, enhanced vertical mixing, and shear between the currents, which also appears to drive the mixing. And it's counteracted by warming from the surface flux, mainly shortwave. And in ICCZ, there's clouds which reduce shortwave and reduce the cooling from latent, tending to warm relative to the annual mean. And then it's mainly the reverse during the other part of the year, leading up to the southernmost ICCZ position, cooling in the north, the sun is in the south, reduction in the currents and the shear on the equator, reduction in vertical mixing, and tend to get slight warming on the equator. So in summary, we found very strong meridional dependence of the heat budget in the northeastern tropical Atlantic. We separated into three different regimes. The trade wind region, 15 to 25 north, has a strong annual cycle of SST. It's mainly solar radiation and evaporational cooling in phase, so that you have strongest warming in the summer, cooling in the winter. And this is damped. We found it's damped by a strong annual cycle of cooling, which we interpret to be turbulent mixing, and which is actually strongest in the summer, counteracting the warming from the sun and from reduced evaporation, and weakest in the winter when you have the thickest barrier layer and a thin mixed layer. Thickest barrier layer, thickest mixed layer in the winter. In the ICCZ core region, farther south, 3 to 8 north, the seasonal cycle is the weakest of the regions that we looked at. There's semi-annual cycles of solar radiation peaking in the spring and the summer. The summer peak is balanced by increased evaporational cooling, and the spring peak seems to be damped by increased turbulent mixing, which we found to be caused possibly by barrier layer and thermocline depth being a minimum during that season. So this kind of counteracting of the solar heat flux by turbulent mixing and the latent heat flux seems to be what is limiting the seasonal cycle to such a low value in the ICCZ region. On the equator, things appear to be a lot different. It's a moderate seasonal cycle, about 3.5 degrees. Solar radiation peaks during the second half of the year. And there appears to be a semi-annual cycle of mixing during May, July, and November, driven by local winds, which accelerate the currents, increase the current shear, and cause more turbulent mixing, although we have very large error bars on our analysis, which should be taken with caution. But it looks like it agrees reasonably well with previous modeling studies and also the microstructure measurements published recently. And finally, last summary slide, last slide. Additional modeling studies, kind of the conclusions, I guess. So that additional modeling studies, of course, are needed to kind of verify and go into more detail on these observational results. And more microstructure measurements would be very helpful to quantify the role of vertical turbulent mixing in the heat budget. And finally, some implications might be that we found that the seasonal cycle of mixing seems to be important even off the equator, especially in the trade wind region, so that it's possible that because the interannual decadal variability is so locked to the seasonal cycle, that in some of these regions that the vertical ocean processes might also be important for longer time scale variability. So this should be looked at in more detail in the future. That's all. Thanks. Questions? Yes?
So I'm really impressed and surprised too about how important mixing is there in the trade with these. It's kind of like a pretty exciting result, I guess.
Yeah, I mean, it's indirect.
Well, yeah, but I mean, not only does it vary seasonally, but I mean, a lot of earlier studies sort of suggest that it really didn't matter. Mixing didn't play much of a role at all in terms of the surface. You've got strong annual mean kind of mixing stuff.
Yeah,
Too.
yeah, I mean,